Okay.
So hello everyone and welcome to the Geoscience and Geoenergy webinar of the 24th of March 2022. So my name is Maartje Boon and I'm a colleague of Hadi at TU Delft, and together with Sebastian Geiger, who is also from TU Delft, I have the pleasure to co-host today's webinar. So we're delighted to host Stéphane Zaleski from Sorbonne Université as our distinguished speaker. Stéphane Zaleski is professor of mechanics at Sorbonne Université and member of the laboratory Institut Jean Leron de Lambert. After early years at the physics laboratory of ENS Paris and the applied math group of MIT, he joined the mechanics group at University of Paris 6. He investigates numerical methods for multiphase flow with applications to atomization, cavitation, porous media flow, nucleate boiling, hydrometallurgy, moving contact lines, and droplet impacts, including several variants of the volume of fluid method, the edge-based interface tracking method, the diffuse interface method, and molecular dynamics. He has written several computer codes for the simulation of two-phase flow, including Paris Simulator, and is an active user of Basilisk platform. Recently, he applied these techniques to the study of COVID-19 airborne transmission by micron-sized droplets. He's associate editor of the Journal of Computational Physics and of Computers and Fluids. He leads the ERC project TrueFlow on mass transfer at large Smith numbers and is a member of Institut Universitaire de France. So thank you, Stéphane, for graciously accepting our invitation. And to the audience, please note that this lecture will last for about 30 minutes, followed by questions. And please type your questions in the chat box, and Sebastian will take them after the lecture. And please do not wait till the end of the lecture to type your questions, but just type them whenever you feel appropriate, as they may trigger other questions by other participants. So Stéphane, we're all looking forward to hearing your lecture, so please start whenever you're ready.
Okay, thank you very much. So in fact, I had planned on 45 minutes, so maybe I would go a little bit fast on some slides, but you can ask me questions later about that. So here is a list of my collaborators. There are many topics, and they're all fantastic people which have made it possible to work on these various topics, such as curtain coating or microlayer and boiling. A lot of these topics are useful in the geosciences, but perhaps the most useful aspect for geoscience is flow in rocks. I have not done recently simulations of flow in porous media or rocks, but this is extremely important. To do this kind of simulations correctly, you need to do the dynamic contact line correctly. The jumps of the menisci in the porous rocks are essentially driven by these contact line problems. And to do some preliminary remarks, the dynamic contact line is a very difficult problem because of the contradiction between the no-slip condition on the substrate and the motion of the contact line. This paradox can be described simply by assuming a linear flow in the wedge, and this leads to a singularity, a logarithmic singularity that was considered unacceptable by people like the old mechanicians. Basically, the only way to avoid infinities is to have this small length scale beta, which leads to a logarithmic ratio that gives you a logarithm for the dissipation, and this beta was considered impossible by Levitch. Later on, Lawrence Scriven expressed this in another way, said even Hercules could not sink a solid. You cannot push a solid into a liquid because of an infinite force now that you have, which is a companion to this infinite dissipation. And so what should we do? Well, we should find a way to regularize a singularity. That's the only mathematical possibility. We have to modify the model of fluid mechanics, or in other words, what we can do is to find what is the nature of the singularity and find an approximate solution near the singularity. And this second problem was solved by Cox, Voynov, Hawking, and Duffy and Wilson. I will describe their solution, which is not completely yet regularizing the singularity. So we have to do more things, as you will see. Let's consider the first problem where you don't have any regularization. If you go in the thin film limit, where h is the thickness of the thin film, you get an equation which is a third derivative of h is 1 over h squared. Assuming h is theta x, curvature goes like 1 over x, and the angle goes like log x. So the angle rotates infinitely in this case. This is unacceptable, and you can use a regularization which is u equal to lambda du dy. Lambda is called the slip length and is measured to be the order of a nanometer or less in many cases. And Voyners have shown that this gives you a modified equation, which is like 1 over h squared plus lambda h. Now, assuming h is like theta x, curvature goes like log x, and the angle goes like 1 over x. And so this is the wrong slide. Sorry, this gives you this gives you an angle going like x log x. So it gives you a finite angle at the singularity. So it is much better in terms of angle and the aspect of the interface, but you still have infinite curvature. So which is in a sense bad, because if you have infinite curvature by Laplace law, you have infinite pressure, and basically the fluid would be boiling near the contact line. So it's still a bit of a problem, but I will discuss it later. So the numerical problem subdivides into 3 subproblems and 2 approaches. So let me discuss the 2 approaches first. The first approach is a microscopic resolved approach, requires grids of molecular size. So this is a little bit like the problem of direct numerical simulation in turbulence. You resolve all the length scales, but it's very expensive. And the other approach, B, is a subgrid approach, which you would use when your grid size is much larger than the slip length lambda, and or maybe at least as large as the slip length. And then there are 3 subproblems: the equilibrium problem, no contact line motion, where we don't have any singularities, the steady motion problem, and the unsteady motion problem. And another point of view on the contact line problem, which is, I must say, a little bit of a philosophical problem, so we have many ways of defining it. The first point of view is, what is a good mathematical model of the moving contact line? The second point of view is, given you have a good mathematical model, how can it be computed assuming infinite computer power? Now, of course, that is very exciting for those of us who like big computations. And then once you have a given model, can we make computations assuming this model with finite computer power? So that's the second approach. I think that not even the first problem is completely solved, and I will explain a little bit why. So what experimental support do we have for the first regularization, the slip model? Well, we have many experiments on the slip, on the Navier slip, and you see in this table that many cases which are marked as no slip, and some cases which are on the order of nanometers. No slip means undetectable, so it for molecular dynamics, it probably means something around 1 nanometer. Okay, so we have to be able to deal with slip lengths as small as 1 nanometer, or maybe much larger. And if we are lucky, we can have much larger slip lengths, up to 10 microns. So given this, with Shoraf-Kami, we started using the volume of fluid method in the octree code JERIS, developed by Stéphane Popinet. And it uses the volume of fluid method. So here is a view of how it works. So I'm going to skip that because it's well known, and basically only tell you that we have this extrapolation in a ghost layer of the Voff reconstruction that gives us the contact angle. So that gives us a static contact angle. And then later on, a Navier boundary condition was added to that by Thomas Fulana. So basically, again, in this ghost layer, we have in addition to the ghost reconstruction, we have a ghost velocity, and this gives us the slip length. We adapted this to a quad tree or octree code. So this is a view of the octree code. You subdivide squares into smaller squares and so on. and then you parallelize this. And so here the colors correspond to the processor, so you can really have a lot of computer power to deal with a very, very small region here. If you have a millimeter droplet and a nanometer length scale, you see that you have a ratio of 10 to the 6 between the smallest scale and the largest scale. So it's extremely difficult, but it is not completely impossible to do. And here, if you have a 1 centimeter length scale, it gives you a 10 to the 8 factor to the nanometer, or 10 to the 7. So, but it is still possible to start doing things. So here's the curtain coating setup. This is an important setup for many reasons that I will explain. It was first studied by T.D. Blake and others. So we have a fluid falling from the top, and you have a substrate here moving to the right at velocity u. So the substrate is going to entrain the fluid. Of course, this is done to create very thin films. If you go very fast, you get very thin films. And it was used a lot in the photographic industry, but it is, for us, it's mostly a very nice controlled experiment about the contact line. And if you go too fast, you get this sawtooth meniscus, you get these bubbles forming, so it defines a critical number. And the critical number is about a velocity of 1 meter per second. And if you zoom on here, you see this kind of foot as in the previous scheme. It was studied a lot by Blake, Bracke, and Shikmurzaev. So I had a photo of my friend Yuli here. The setup was used to argue against a local mobility law, a law that would tell you that the contact angle is a function of the velocity. So the numerical proof of that by Yuli and others was based on huge finite element simulations, and based on the fact that they could not reproduce this experimental point here, the pluses, by the numerical points here, the continuous lines. And so the apparent angle is matched to the experiment, and then you redo the simulations at various values of v. So you match it here, and then you redo it at various velocity v, and apparently it fails. And this is a close-up of the smallest length scale at 20 nanometers. So they did go down to less than a few nanometers for their finite elements. But new simulations were redone by Liu, Vandre, Carvalho, and Kumar of this system. And in fact, it depends a lot on the viscosity ratios. So these three curves, the blue, the black, and the green, at various viscosity ratios. And in fact, you get very different results. So that puts some doubts on the simulations of Yuli because of that. So we decided to try again. And we do the same system as Liu, Vandre, and Carvalho. It's a reduced system where the height is not 3 centimeters by 1 centimeter. And so here's a view of our simulation. You see how we can refine here the contact line. We have 3 zoom levels, and finally we get these very small grid sizes here. We use the slip length, and in that case, we get a convergence of the interface position and inflection point position at second order. We have this little triangle that shows us it's the error, and it goes to 0 like second order. And we reproduce almost exactly the Liu et al. Finite element calculations. We can also do the same comparison that was done on the apparent angles. So this was a comparison of the transition from the steady regime to the corrugated regime or the unsteady regime. And this is a comparison of the apparent contact angles. So we did them for several Reynolds numbers. Liu did only a single Reynolds number, but we show here that it depends also a lot on the Reynolds number. So these are all the examples. We see different configurations in this diagram of capillary number based on the plate velocity and Reynolds number based on the flow rate. We have 3 different points with 3 very different geometries, but all of this works nicely. And then we decide to compare it to 2 other experiments, the Blake experiment again, now with a larger height, 3 centimeters, and the Marston experiment, which has the advantage of having a very large slip length. And so, again, it works nicely, but in that case, we perform a cardinal sin. The slip length not resolved. The slip length is officially experimentally believed to be near 5 nanometers, and we use a grid size which is much, much larger than that. So these simulations are not well resolved. They are anti-DNS, so to speak. And for the Marston experiment, it's much nicer because we can resolve the slip, and actually it works better also, the comparison with the experiment. And with Liu is much better. And so we go back to this comparison with the Blake experiment, and with new efforts, we have reduced even the slip length while keeping the grid size much smaller than the slip length. So these are resolved simulations, and we see that the capillary number of the transition varies a lot with 1 over lambda. So we hope to find a trend. This is an unfinished work. This is a preliminary result. We hope to find a trend to extrapolate this to very small slip lengths to try to match the Blake experiment. Another result of this huge computational effort, which involves a lot of grid points smaller than the slip lengths, as you can see here. Here we have really 100 grid points and slip lengths. You start seeing this logarithmic singularity of the curvature. So you see this kappa, which is growing with lambda as we refine the grid. This has given us a lot of results, but this is a complicated setup, and we would like to try a simpler setup. And so you could do plunging plate experiments, and there we have some scaling laws which were found by Jens Eggers and Benny and Timson, but this is still work in progress. You could reverse the plunging plate and do, but here I can show you some preliminary results. We approach the m equal 1/2 slope. So we have m equals 0.6 for the largest capillary number. So we think we can understand the scaling and the possible extrapolations soon. These were all kind of resolved simulations where we had lots and lots of points inside the slip length. How could we do a subgrid simulations and investigate the singularity that arises in the no slip case? Well, we do this with withdrawing plate experiments, and in that case, Cox and Voynov had predicted a law of this kind with G, this function, this complicated function G. And I suggest to revisit that theory by, instead of having the equilibrium angle here, having here an arbitrary dynamical angle, which occurs at the small length scale. And Li is not necessarily the slip length, but some summary of the effects of the microscopic physics. And then we consider that, and we do the withdrawing plate simulations. So here we have some example of the withdrawing plate simulations. The result of the withdrawing plate simulation is that we have a transition for a situation that there is no Landau-Levitch-Deriagin film. The contact line stays at constant height, and a situation where the height of the constant contact line, which is plotted here on this vertical, the height of the contact line grows without limit. So there is a transition between the two, which defines a critical capillary number. So it's the same idea of a critical capillary number as in the curtain coating, but here instead of entraining air, you are entraining liquid. So it's a receding contact line. And you see here, when you do this, that the critical capillary number depends on the ratio of the grid size delta and capillary length LC, the gravitational surface tension length. And so to understand that, you have to use the Cox-Voynov theory. And the interior length scale that appear here in the numerical case depends on the numerical small scale parameter, which is the grid size, times some gauge function phi, which is known to be this E over theta over 3 in the lubrication case. And we can try to verify that. And we actually see that. We see a logarithmic dependence, but it doesn't have quite the right slope, which comes probably from the fact that we don't have a wide enough range of scales. For larger angles, it works a little better. And what have we gained with this? We can verify the Cox law approximately in some cases. We were also able to see the wetting transition. I don't have the time to show you this. And it also provides us a subgrid scale model that I will describe a little bit later. But we didn't have good experiments on the withdrawing plate. And so we decided to replace the experiments with some molecular dynamics. And so we did that with a group of people at KTH, called the KTH shear droplet experiment. So the experiment looks like this. We have a much smaller scale now because we cannot do molecular dynamics at huge scales. So now the height has gone from 3 centimeters to 50 nanometers. It's a radical change. We have relatively small capillary numbers, and we use molecular dynamics to serve as a virtual experiment, and we compare it to 2 types of continuum mechanics method, the phase field methods of Hamburg and the volume of fluid as before. The system has 4 contact lines, 2 advancing and 2 receding. We use a localized Navier boundary condition coupled with a constant contact angle, but the Navier boundary condition is, you will see, is not very useful here because the MD has a very, very small slip length of the order of a nanometer. So this was, there are 2 papers on this. There's this paper I'm citing here, and there's another paper which has been accepted in Journal of Fluid Mechanics, which is also available on arXiv. So the parameters are here. The viscosity is the density. So the vapor density, it's a water in equilibrium with vapor. The vapor density is very small. The viscosity of the vapor is also very small. The surface tension is in a reasonable range. We use a modulated Navier boundary condition with a Bell function d over epsilon. The contact lines are determined by the specific choice of the potentials in the molecular dynamics. So they are given here. This is a view of the MD model. We have in the solid, we have silica atoms, molecules, and in the water, we have water molecules. The molecules form hydrogen bonds, which suppresses the slip. A lot of people before had done Leonard-Jones MD models, but which have slip. So to study that, we, in addition to VOF, we had another point of view, which was first advocated by Yves Pommeau, who has unearthed all the simulations by Pierre Seppercher. Pierre Seppercher did his thesis in my lab something like 40 or 50 years ago. And he has written this paper. 1996, no, that wasn't 50 years ago. That was only 36 years ago, or no, 26 years ago. But so I'm always exaggerating by a factor of 2, as you can see. But he obtained this very nice contact line showing the density field. So the iso line of the density fields gives you the position of the interface, a bit like the current famous level set methods. And it's a diffuse interface method where you see the interface has a certain thickness. You use a free energy with a double well potential. And that is simpler than Seppercher. That's the Jackmin and Hamburg model. You have van der Waals expression for the effect of the gradient on the free energy. And you relate the order parameter C to the density rho and to the viscosity mu. you get a set of complicated equations. The first one is incompressibility. The second one is like Navier-Stokes with this new surface tension term here. The third equation is an equation for the Cahn-Hilliard equation for the order parameter. And phi is called the mobility, and it's also a function of the Laplacian of the order parameter. Phi is the chemical potential, and kappa, the coefficient that gives you the flux, is the mobility of the model. The bulk free energy is again the double well. And the boundary conditions are very complicated. They are obtained thermodynamically as the only possible boundary condition that satisfy the Onsager relations. And they give you a motion of the order parameter, motion of the interface, even in the case of no slip. So you perform this regularization miracle by having motion of the contact line even with no slip. And so these are some examples of the simulations of this. And you can see that the reason the interface moves is that you have this flux, you have these thin white arrows that show that there is an evaporative flux through the contact line region. So that, of course, the evaporation will make the contact line recede. And that's what makes contact line motion possible, even in the absence of any slip. And so we perform that. We perform the MD simulations, the phase field simulations with the model described, the volume of fluid simulations as previously. This was done in this case by using Basilisk. And you see that there's a perfect agreement in the center, but in the boundaries, the agreement is very imperfect for both the phase field and the VOF. They don't really follow the MD, especially here near the advancing line. The receding line really don't match with the equilibrium angle theta zero. Theta zero is the equilibrium angle, and pi minus theta zero is the equilibrium angle on the other side. So you have to do pi minus theta because it's on the other side. So you can have very strong variations, but they are not those which are obtained. So the story is not quite finished yet. So maybe we should use a compressible system. So I've written here the compressible equations. And we have actually, Alexandre Limaret had implemented this in Basilisk, so we can now have a contact line with the van der Waals model. But we don't know whether it's going to be better for that. The phase field also allows us to derive a new regularization, the Tizikian GNBC. And so this looks like the Amberg conditions, but Tizikian replaces them by these conditions here. And especially you have now a coupling, instead of no slip, you have a coupling of the velocity and the L of C term, which is the right-hand side of this, which is this. The L of C term is called the uncompensated Young stress. Remember, the Young stress is what fixes the static contact angle. So this can be understood using the Tench planar interface solution, and it leads to this condition I've written again. The new condition is the combination of the Navier slip condition, if you put this to 0, and the surface energy relaxation is called the GNBC. And the other condition we have for the other parameter is identical to the Amberg and Jacquemin condition. So expanding the GNBC near the Tench solution yields an expression like this, with F epsilon is now not a function of the other parameter, but an explicit function of Tench H. It's like a regularized delta function. And now you have steady state contact line motion possible, and a simplification occurs the x equal in steady state, d theta dt is 0, and we get the contact line velocity as a function of the GNBC parameters. So that's a very nice result, which shows that you completely eliminate all the singularities, and as you could not do with just the simple Navier slip. I have here a note that GNBC has been used by many authors to do actual simulations in the Gerbeau and Lelière formulation, where you actually use the real delta function and not a smooth delta function. So as you refine the grid, the delta function has the width of the grid size, and gets worse and worse as you refine the grid. and they have a kind of fake convergence of the delta function GNBC of Gerbeau and Lelièvre. So that's not the GNBC I'm advocating. So instead, we would like to use a smooth GNBC, and we have some work in progress on that. So finally, going back to the third problem we have, can we make computation with finite computer power? We suggested something in 2009 for that, and Lejeune and Maglio restarted that. We suggested using the Cox relation again, so I've written it again. And there are other subgrid ideas that I'm also working on, like subgrid evaporation, but I will just talk today about the Cox approach. So we distinguish three regions: an inner region, an intermediate region, and an outer region. And in the intermediate region, we have the grid scale. It's in the intermediate region, and then we implement a numerical contact angle at the grid scale, which is numerical contact angle theta delta is given by the Cox theory by using this equation. And Lejeune and Maglio actually developed three different models using the Cox theory, where they have three length scales: the outer length scale L, the inner length scale lambda, and the slip length lambda. So this actually here should be LS. And so I know it's a bit confusing, but please bear with me. So the DIN1 model of Lejeune and Maglio has the outer scale, which is fixed. This is not good because it should depend on the grid size. The DIN2 model has a slip length which is 0, which is not good either. And the DIN3 model has a fixed inner length scale, so this is fixed, and an outer scale with the grid size and a slip length which is also the grid size. So this is the best of the three Lejeune and Maglio model, and it is shown to allow converging simulations of problems such as this spreading droplet. So we redid this with Thomas Fulana, and we found that in fact this leads to a strong oscillations of the contact line and the velocity. So we're currently what we are trying to improve this DIN3 model by smoothing, increasing the smoothing of the slip model, a bit like with what is done with the GNBC. We can also try to reproduce experiments by Lavie and Marmor on spreading droplets. You see here that as we refine the simulations, we have these kind of jumps that become smaller and smaller, but they're still a bit worrisome, so we're also working on that. So what does it teaches us? There is a region where Cox have a range of validity, a micro scale and an outer scale. And the outer scale, for example, in the shear droplet is the thickness of this slab obtained by the MD. And for the Cox theory to be valid, we need the capillary number to be much more than 1, and the outer scale H to be much larger than the inner scale L sub I. But the second inequality has to be obtained in logarithmic sense. And so in fact, H over Li has to be exponentially large as 1 over Ca. So this requires you to have huge ranges of length scales, which is not always possible. And moreover, we have additional difficulties with this subgrid approach of based on the Cox law, and which is apparent in the curtain coating problem, is that the Reynolds number remains large even in the region which is much smaller than the outer scale and getting close to the micro scale. So, for example, this Reynolds number effect, this red blocking region, makes it impossible to use the Lejeune and Maglio approach or the Cox approach that we had in, for example, the curtain coatings, curtain coating case, or in many, even perhaps probably in this shear droplet case. And so this is the end. We have not completely solved the problem. As I said there, we are not even sure we have a good mathematical model of contact line, but probably this model will be found soon based on MD simulations, phase field simulations, and new ideas such as the GNBC or evolution of these new ideas. So that's the end of my talk. And I'm going to leave the presentation mode so I can see you people.
Yes, please do so. I seem to have just lost Martje, so I start out. Thank you very much, Stéphane, for a really interesting talk. And we have quite a few questions coming through already, and I do hope we get Martje back in a moment here. So the first one is from Julian Mays. He says, "Hi, Stéphane. Thank you for the great talk. Your capillary numbers are always larger than 10 to the minus 3. Does that mean slip doesn't have an impact at low capillary numbers?"
No. At low capillary number, you have a lot of impact, and you can a low capillary number, you can apply these theories in principle. The difficulty with very low capillary number, as you know, because we have more or less worked together on this, is that you also have special numerical difficulties called spurious currents. And in fact, we believe that for these very low capillary numbers, we will be able to reduce the spurious currents. We have a so-called better numerical model. So if you use things such as very smooth conditions, such as the GNBC or a smoother slip condition, then we will be able to also do the very small capillary numbers.
Okay, thank you. Go over to Moitaba Nurusi. He says, "Hi, thank you for the interesting talk. Why not
Can you
use
go back to the question of Julian Mays? Just 1 second, please.
Yes, of course.
Maybe I misunderstood it. Yes, always larger than 10 to the minus 3. Yes, in this book, they're always larger than 10 to the minus 3, but we have smaller numbers too. Okay, yes. Sorry, I was not sure. I'm not confused the answer, but it's okay.
Okay.
So please move on to the next question.
Yeah, of course. Moitaba says, "Hi, thank you for the interesting talk. Why not use variation in interfacial tension instead of using a slip length to avoid singularity at the three-phase contact line?"
Oh, that's an excellent question. Well, that's a very, very good question. Well, the question here is this variation going to occur over molecular scales, like the nanometer scale, in which case we will be able to deal with it in a similar way as we deal with the other nanometer scale length scales? Or is this variation going to happen on a much larger length scale, such as advocated by Yuli Shikmurzaev, who thinks that it will occur even at time scales of the order of milliseconds? Basically, for Yuli, interfacial tension rearranges with a time scale of a millisecond, which other people don't believe. So the question is, to answer your question, I need to know at which scale do you want to look at these interfacial tension variations? And depending on your answer, I will tell you yes or no. Basically, if you tell me it happens on a larger scale than on the millisecond scale, I will tell you I don't believe it. I don't believe it's true for pure fluids. I don't believe that MD shows anything of the sort. But if you tell me it happens on the nanometer scale, then I would say yes, why not? We could try something like that.
Thank you. Willemijn asked a question. Thank you, and also says, "Thank you for the interesting talk. You mentioned that the scale of molecular dynamic simulation is much smaller than other simulations. What kind of difference would you expect based on this? I guess what kind of difference in results would you expect based on this difference in scale?"
Excellent question. I don't expect to see differences, and I believe the MD are not very different from the actual experiments. What I expect to be able to see what happens on these scales, which I cannot see in the experiments, except if I have very, very clever experiments which show me what happens on the nanometer scale, and there are not many experiments like that. I don't expect to see anything different. I expect to see more, not different.
Okay, thank you. Stefan Berg asked, "For very rough surfaces such as a rock with partial wetting, where you likely have pinning effects of the contact line at very specific locations. What does this mean for the dynamic contact angle?
That's an absolutely excellent question. Well, this is the next step, you see. Suppose we are successful, we find a quote-unquote good model of the contact line, maybe a very clever GNBC model or something like that. Once we have the good model, or once we have a reliable phase field model, for example, then we can modify our problem, and we can, instead of having this smooth boundary condition at the bottom, we can do rough boundary conditions, and we can use our good model on the rough boundary conditions. And then we can answer your question for roughness at the nanometer scale. Now, if you mean roughness at the micron scale, this would be easier, because maybe we can do something which is not too bad at the micron scale. So if your question about roughness at the micron scale, then we can do it, and probably already people doing that. And what we expect, well, we have people doing that, and what they see is they see the contact line jumping from roughness point to roughness point, as you say, from pinning point to pinning point. And you can say, is this, well, I mean, then you can ask, is this correctly computed? Probably yes, if we have a not too bad model of the contact line.
I'm going to switch to a question from Florian Doster, and so follows a little bit up on what Wellman asked. Says, thanks, Stéphane, for a very exciting talk. Are there any experimental approaches that are able to test the understanding across scales, or are impurities, heterogeneities uncontrollable?
No, I think there are good experimental approaches. There are some people who have done AFM microscopy, atomic force microscopy, and have found really interesting things like precursor films, nanometer, one molecular layer of precursor film. Yes, you can. People are beginning to do that. I guess it's a race between them and us. Do we do interesting things with MD first, or do they find lots of answers and interesting things doing these experiments first?
Thank you. Julian Mays has another question, and it's a two-part two-part question. It says, what about time stepping? Because of the capillary time step constraints, when you increase mesh resolution, we need to reduce time steps with an order 3/2, making it very small very quickly. Is the solution implicit time stepping?
Very good question. Because most recently we were working on the curtain coating problem, where the capillary number is rather large. The viscosity is large compared to the surface tension. So this helps with this capillary time stepping problem. So we don't have too much of these problems. We are not working on this, but there are other people then in our group who are working on implicit methods for the capillary time stepping that would, if successful, resolve this problem of the very small time steps. And so, if you write to me, I can put you in touch with these people.
So yeah, I think Julian probably heard that comment. So expect an email then from Julian, I guess, in due course. I don't see any further questions coming through from the chat. I don't know, Marty, if you have any questions, and if not, we can thank you, Stéphane, for a really interesting talk. Thank you to the audience for some excellent questions. Marty, if you have any questions yourself as a post.
No, I don't have any questions right now. Thank you.
I hand over to you for some closing remarks.
Yes, so thanks again for a very, very interesting talk. So I'd like to take the chance to introduce our next week's speaker. So next week we will host Anna Scotti from Politecnico di Milano, who will speak about mineral dissolution and precipitation in fractured porous media. So until next week, and as Hadi says, stay happy, healthy, and tuned in to our Geoscience and Geoenergy channel. Thank you, and see you next time.
Thank you, everyone. Bye-bye. Thank you, Stéphane.
Goodbye. Thank you very much. Thank you for the interesting questions.